This is the 19th video of the lecture series Optimization using Excel, and in this video I am planning to give you some introductory features of nonlinear programming. In this video I am not going to discuss any problem or any formulation or any Excel work. Rather, I will give an introduction to what a nonlinear programming should look like and what are the various features we need to learn. Now, I have already discussed in my linear programming introduction video that what is the difference between linear and nonlinear models. So, you should remember that for a linear model, always the decision variables, both the objective function and the constraints, are in the linear form. And what do you mean by linear form? That means if x and y are your decision variables, then the constraints and objective will be in the form of ax plus by. And what is a and b? A and b are constants. So objective and constraints, all the constraints and the objective also must be in the linear form ax plus by. Then only we can say that the problem is linear. Otherwise, for every possible opportunity, for every other function, every other format of the objective and constraints, the problem is non-linear. What are the example? Example can be x to the power n, like x square or x cube or x to the power 4 or anything. X into y, like x multiplied by y, that means the product of two decision variables, if that is also there. Then log or square root, sine, absolute, every kind of other possibilities will give a nonlinear function, and in that case the problem will not remain linear. We'll call that it is a nonlinear program. And this also includes the function of Excel also, nonlinear functions like, as I have mentioned here, if, choose, lookup, hlookup, vlookup, count, integer, round, ceiling, floor. All these functions are nonlinear functions in Excel, and logical functions also. These are nonlinear, and therefore if you have used these functions in your model, then the problem cannot be solved using simplex LP, and it will be a linear, it will not be a linear program, it will be a non-linear program. So let us come to the next slide. Now in the next slide I have given an introduction of what is convexity and what is concavity. So if there is a function fx, then we will call it a convex function if the line joining between x comma fx point and y comma fy point, means the 2 points on the function line, and if we join these 2 points with a line, straight line, we also call it as a chord. This is also known as a chord. So if that chord is above this function line, the line of the function line representing the function f, so in that case the function will be known as a convex function. Otherwise, if the situation is exactly opposite, that means the chord, your chord is below the function line, the line representing the function f is above this chord, in that case we will say that the function is a concave function. But most commonly the function may not be entirely concave or convex, so you can see this type of constraints. For example, sine constraint, sine x, if you plot sine x, this type of function will appear. So if you see this type of graph, that means it is neither a complete convexity nor a complete concavity, so we call it non-convex, which means the function is neither convex nor concave. In different parts of the in different ranges it is either convex or concave. So okay, that is fine, but why are we discussing all these things? Because you see, the method of solving or the ease of solving depends on whether the function is convex or concave. So if the function is convex, and more specifically if the functions that are there in the constraints are convex, and the objective is also convex for maximization problem or concave for minimization problem, then we can say that the solution, the nonlinear solution, the method of solution becomes easy for the solver, and there is a high chance that you can get a global optimal solution. But still there is no guarantee of getting global optimal solution. For getting guarantee, we have to go to the next slide. And just a quick note here that all linear models are by default convex, and therefore they can be solved very easily using solver, and specific simplex LP solver is given to you in order to solve them. Okay, so let us come to the next slide. In the next slide, we have again discussed another feature, which is the smooth versus non-smooth function. So what is the definition of a smooth function? The function is smooth only when the function and its derivative. What is the derivative? Derivative means ddx of fx. ddx of fx is the derivative if both f and f prime are continuous. What do you mean by continuous? Continuous means it has not got no breaks in between. So if that is the condition, that means f and f prime are both continuous, then we will say that the function f is smooth. Now what are the examples are, these are the some of the examples of smooth functions, like 1 by x, x to the power n, log x, square root of x, and so on. So for example, if you plot x and the function is log x, then the function will look something like this. This is log x. So you can see that at every value of x, the function is obviously non-linear, but it is continuous. There is no break. If you take any value of x, you get a particular value of the function. And if you plot the ddx of log x, that means the f prime or the derivative of log x, then also you will find that the function is, that derivative is continuous. So since both log x and its derivative are continuous, we can say that the function log x is a smooth function. So therefore it implies that continuity and smoothness are not the same thing. So basically what I try to say here is continuity does not imply smoothness. So there can be continuous and still non-smooth function. What is an example? An example is absolute function. If you take the absolute of x, it is a continuous function, but it is non-smooth. So therefore another thing you can say from here is that discontinuity will imply non-smoothness. If a function is discontinuous, you can say directly that it is non-smooth, but continuity cannot imply smoothness. So let us try to understand the non-smooth behavior. You can take the example of this function. This is an if function. This is saying that if x is greater than 1, then the function gives you y. Otherwise, if x is not greater than 1, that is less than equal to 1, then the function will give the output 2 into y. So now you see the graph of this function will have a break. How? Because at x equal to 1, you don't know what is going to happen. So there will be a break and the rate of change is also unknown. And so the derivative of this function cannot be computed at the point x equal to 1, and hence this function is discontinuous and non-smooth. So we have already discussed convexity and concavity. So in the last slide I told you that convex functions in constraints and convex objective for maximization or concave objective for minimization will imply easy solution, easy nonlinear solution. But in addition to that, if we can ensure that the function is smooth as well, so smooth function in the objective and constraints, that will imply global optimal solution. So I repeat once, if you can ensure two things, one is this, two is this. What is one? That the function in the constraints are convex and objective is convex also if maximization, or the objective is concave if minimization, and the function is a smooth function, then you can be sure that you are getting a global optimal solution. Otherwise, for any other possibilities, you are not sure that you are getting a global optimal solution. You will always get a local optimal solution. So the solution is giving you the minimum or maximum value in a particular location. So you consider any area outside that location, there may be another maxima which the solver or the method is unable to find for you. So this is it, and let us move to the next slide. In the next slide we have discussed the solvers that Excel has given to you for solving nonlinear problems. So basically there are two solvers. One is your GRG nonlinear solver, another one is evolutionary solver. So let us discuss these two solvers, how they are trying to approach your problems. So the GRG solver, this is the most commonly used solver, and it was used until the Excel 2010 version. So like the previous version was like, I think it was Excel 2007, and up to that we had only the GRG solver in the Excel, and it stands for the Generalized Reduced Gradient. The full form is Generalized Reduced Gradient. And how it works, it starts with the initial point, initialization, that means any random starting point it takes, and then it calculates a gradient. So for example, this is the starting point, assume that this is the starting point, and it takes a gradient at this point. Now suppose this is the starting point and it takes a gradient at this point, and what happens, this is the step 2. So first it takes a arbitrary point and calculate the gradient at that point, and it moves in that direction for which the gradient will be minimized. So by default we are talking about minimization problem. So it will try to reduce the gradient, and if you see, this is a convex function, and you can reduce the gradient only if you go downwards. So if you go upward, the gradient will try to increase. So it will come downwards by reducing the gradient, and then it will repeat the process. So it will come downwards, then come further downwards, and then it will stop at a point when there is a maximum number of iterations already performed, and your step size is smaller than the tolerance. So if that condition is achieved, then the solver stops there, and this is the generic idea about how the GRG solver works. Now let us come to the next slide, where we have explained the evolutionary solvers working mechanism. Basically it is introduced in Excel 2010 onwards, and it is working based on the concept of genetics, evolution, mutation, and survival of the fittest. So how is it different? Very firstly, unlike the GRG solver, which always starts with a single point and tries to improve that. Uh, and you note that for GRG solver, the solver always takes care of one single point at a time, one single solution at a time, and tries to improve it, and then goes to another point that is also a singular point. But in this case, for evolutionary solver, the solver starts with a population of, that means several number of possible solution it populates. And then what is the next step? Next step is the fit members of that population is allowed to produce offsprings. So what do you mean by fit members? Fit members means the solver tries to test the fitness by verifying the objective functions. So the objective function values and also the constraints. Also it tests the constraints feasibility. So for example, some of these solutions in the population will not meet some of the constraints, so it will put higher penalty to those solutions, and therefore they will not remain fit. And similarly for the it will verify the objective function value for all the members of the population, and the members which are giving you not so satisfactory objective function value. So for example, if it is minimization and the member is giving you higher values like maximum values, then those members will also not be fit in the introducing the offspring. Okay, so what is an offspring? Don't get confused. Offsprings means, suppose these members are coming from various cells in the Excel sheet. So while producing offsprings, the outputs from different cells are mixed. So suppose two solutions are there and two solutions have x and y. So solution 1 have x1 and y1 and solution 2 has x2 and y2. So x and y are decision variables. These are decision variables. So this is the first solution, this is the second solution. Suppose in your population there is only two outcomes. So what is an offspring? Offspring will be x1 and y2. So they will mix the outcome of the two solutions, and the mixture will be called an offspring. And all these offsprings will create a new generation. So first of all, there was a population, initial population, then offsprings were created and the new generation. So that is a new population or a new generation will be created from the offsprings. And this process will continue to happen for a large number of time, and this will stop eventually when there is no significant improvements are obtained between several consecutive generations. So this is how the evolutionary solver works. And there is also a concept of mutation. The offsprings will be produced from the population and the solver will change some of the offspring. So change some of the offsprings randomly within that generation of offsprings, so that the property of those offsprings become radically different from the others. So that way it is a mutation, and it ensures that there are not only local optimal solutions are found, there is a high probability that we get the global optimal solution from the procedure. So this is how the evolutionary solver works, and although it can be used for any type of problem like linear programming, smooth continuous functions also, but it is recommended that you use that for discontinuous and non-smooth functions, because for other functions like smooth functions, continuous functions or linear functions, you already have simplex LP and GRG nonlinear which works very well and efficiently fast. If you use a genetic algorithm or evolutionary solver, it takes a little more time than compared to those two solvers, and therefore it is not recommended to use it for linear models or for smooth or continuous functions. So please use this evolutionary solver for discontinuous and non-smooth functions. So what is discontinuous and what is non-smooth, I have already told you in the previous slides. So that's all about nonlinear programming, and in the next video we will discuss one type of smooth function and try to solve it using GRG nonlinear. Until then, goodbye and thank you for watching.